In this video, let's talk about alphabet, language, regular expression, NFA and DFA. Let's start with an alphabet. An alphabet contains a set of symbols used in a language. For example, the English language contains the alphabet A, B, C till Z, as well as capital A, capital B till Z. Another example is the binary alphabet, which contains the symbols 0 and 1. Now let's talk about a language. A language contains a set of strings over some fixed alphabet. For example, let's see the language containing strings over the alphabet 0, 1, which starts with 0 and ends with 1. Now let's write the strings of this language. The language contains all strings starting with 0 and ending with 1. So the strings can be 0, 1. This is one string, a minimal string in which the first character is a 0, that is, it's starting with 0 and ending with 1. We can write so many other strings satisfying this condition. For example, 0, 0, 1 is also a string that is part of this language. The first character is a 0 that starts with 0 and ends with 1. We can also write a string 0, 1, 1 wherein it starts with 0 and ends with 1. We can write the string 0, 0, 0, 1. Here also the starting character is 0 and the ending character is 1. We can write 1, 0, 1, 0, 1. Here also the starting character is 0 and ending character is 1. Satisfying this condition, we can write so many strings. So all these strings represent the language. All these strings are part of the language. Now let's see about regular expression. A regular expression is a pattern that matches the strings. A regular expression represents a regular language. These are some of the valid regular expressions. A is a valid regular expression. AB is a valid regular expression. AB is the character A followed by a character B. We can write A or B. This is also a valid regular expression. A, the character is either A or B. We can also write A or B the whole star, which means 0 or more times of A or B. We can also write A or B plus, which means 1 or more times. Star stands for 0 or more times, 1 stands for 1 or more times. Let's go back to the same language, which contains strings of zeros and ones starting with 0 and ending with 1. Let's try to write the regular expression. So the first character is a 0. The last character is a 1. In between, there is no condition given. It can be either 0 or 1 any number of times. So the first character is 0, starting with 0. The last character is 1 because it's ending with 1. That we know. But in between, it's not said whether it should be 0 or 1. So how many characters between this 0 and 1 also we don't know. So it can be 0 or more times 0 or 1. So we write that 0 or 1, 0 or more number of times. So 0 followed by 0 or 1 the whole star followed by 1. So this is the regular expression that matches the strings of this language. Now let's talk about NFA. NFA is non-deterministic finite automata. A finite automata is an abstract machine that is used to represent a language, a regular language. An NFA contains a finite number of states with a start state, and it can have one or more final states. And also we have transitions from one state to another state. Now let's go back to the same regular expression which represents a language that starts with 0 and ends with 1. We'll now try to draw the NFA corresponding to this language and regular expression. So it has a initial state. So it starts with 0. So we draw two states. One is the start state and we have another state which is the next state. On input 0 it goes to the next state. On input 0 it goes to the next state. Then we have 0 or 1, 0 or more number of times. But it is a repeated one because 0 times it can be present, or it can be present 1 time or 2 times or any number of times. So we have to have a loop which states it can be 0 times, meaning that it will be in the same state, or 1 times or 2 times, however times we want that to be. So what is the input? The input is either 0 or 1. So the input is either 0 or 1. Then after this we have a transition to the next state wherein the input is 1. So after reaching this 1 we have no more inputs. So that is all the string. So we have reached the final state. The final state is represented by a double circle. So we can give numbers for the states or names for the states. So I give 0 for the state, start state, and 1 for the intermediate state and 2 for the final state. This is called NFA because it is non-deterministic, meaning that on any input from one state it can go to more than one next state. For example, from state 1, if we take from state 1 on input 1, we can see it is going to state 2. That is one transition. Another transition is from state 1 on input 1, we have the transition to state 1. So the next states to state 1 are state 1 and state 2. So we can have more than one next state. That is possible in NFA. Next we are going to see about DFA. DFA is deterministic finite automata. Both NFA and DFA are finite automata, meaning that there will be finite number of states. An automata is an abstract machine which represents a regular language. How we differentiate NFA from DFA is NFA can contain more than one next states on a particular input, whereas in DFA it is deterministic, meaning that from a state on a particular input, the next state can be only one. We cannot have more than one next states on the same input. Now consider the same example as we saw in this NFA. In this NFA, if we see from state 1, we have two transitions. One transition is going to state 2. So the next state is 2. Another transition, it goes from 1 to 1. That means the next state to 1 is again a 1. So if you see the input 1 from state 1, on input 1 it goes to two states, state 2 as well as state 1. So it is non-deterministic. It cannot be considered as a deterministic finite automata, because in deterministic finite automata, the next state on a particular input from a state can be only 1. It cannot be more than 1, as we see here in this NFA. So now let's try to draw the DFA for the same language. Now let's again see the strings which are permissible in this language. The minimalistic string is 0, 1, which starts with 0 and ends with 1. We can see all the other strings like 001, 0001, a lot of zeros followed by 1. All those strings are permissible in this language. Also, we can see 0 followed by so many ones, 011, 0111, 01111, like that. All those strings are permissible in this language. Also, we can see 0101 is permissible in this language, 0101, 0101, like that. All those strings are permissible in this language. So let's try to draw the DFA with the minimal string. So we'll have a start state. We can have a transition. For the minimal string, the first character is 0 and the last character is 1. The first character is 0 and the last character is a 1. Now we'll take the second string. Now when we get this, the first string 0, 1, 0, 1. If we get to this state, we'll number the states, state 0, state 1, state 2. And when we reach state 2, that is all. We don't have any more inputs. So this can be taken as the final state with double circles. Now we'll try to see whether the second string is also able to be represented by this DFA. The second string is 001. 0. First 0 is there. Second 0 is not there. 1 is there. So what we can do? We can have a 0 in the middle. So we can write 0, 0, 0, 1. And if we see 0001, that is the third string, 0001. The third string is 0001. That can also be represented by the same NFA, DFA. That is, first character is 0, the second character is 0, it comes back again to state 1. The third character is also 0, again the transition comes back to state 1. The last character is 1, so from state 1 the transition goes to state 2, which is a final state or accepted state. So the third string is also acceptable. So how many zeros are in the front before a 1? All those strings will be acceptable by this DFA. Now let's go to the fourth string. So the fourth string is 011. In that case, it starts with 0. On input 0 it goes to state 1. On input 1 it goes to state 2. And at the last we have input 1. For that we don't have any transition here. So we can modify this DFA by adding that transition. So we add a transition to represent the fourth string 011. Okay, now let's go to the fifth string 0111. So the first 0, it goes from state 0 to state 1. Then on input 1 it goes from state 1 to state 2. Then for the next one it goes from state 2 again to state 2. For the third one it goes from state 2 to state 2. So it is acceptable. So in this case also, in which the first character is a 0 followed by any number of 1s, all those strings will be acceptable by this DFA. Now let's go to the string 0101. In this case, the first character is a 0. It goes from state 0 to state 1. The next character is a 1. It goes from state 1 to state 2. The next character is a 0, but we don't have any transition from state 2 on input 0. So we will modify this DFA to include this. So from state 2 we don't have any transition on input 0. So we'll add that transition on from state 2 on input 0. It goes to state 1. So when we see this on input 0, the first character is 0, it goes from state 0 to state 1. The second character is state 1. The second character is a 1. So the transition is from state 1 to state 2. The third character is 0. It goes from state 2 to state 1. Again, the fourth character is a 1. It goes from state 1 to state 2. Finally, it is the accepted state. So always we should be able to start with the start state and should be able to end with the final state or accepted state. So we are able to do this. So this string is accepted. Finally, if we see this string 010101, that is also acceptable by this DFA. So all such strings, all such combination of strings are accepted by this DFA. So now let's check whether this is deterministic finite automata. So deterministic means on a particular input from a state there should not be more than one next state. So from state 0 on input 0 it goes to only the next state 1. From state 1 on input 0 and input 1, on input 0 it goes to state 1, on input 1 it goes to state 2. So only one next state. Similarly, from state 2 on input 0 it goes to state 1, on input 1 it goes to state 2. So we are not having more than one next state. So this is a DFA. Now let's take another example. The language is a set of strings over the alphabet A, B, which contains an A as the second character from the right. Now let's try to write the regular expression. Here it says the second character from the right is an A. All other characters, it can be anything. That is how it is given in this language. The only condition given is the second character from the right is an A. So this is the last character from the right. This is the second character from the right. And these are all the previous characters, preceding characters. So the second character from the right is this. It says the second character from the right is an A. It is not said about the last character. The last character can be any of the symbol from the alphabet. The alphabet contains A and B, A, B. So it can be either A or B. The last character can be either A or B. So we can write A or B. And what is said about the previous characters or the preceding characters? Nothing is said here. So the previous characters can be any number of characters and it can be a combination of A's and B's. So the previous characters can be any number of characters. So we can use a star. It can be 0 characters or 1 character or 2 characters or 3, 4, 5, anything, any number of characters. So it can be a combination of A's and B's. So the previous characters can be A or B. How many characters can be there? Any number of characters. So to represent that, we write star. Star means 0 or more number of times. 0 or more number of times of A's and B's. Now we'll write the NFA for corresponding to this regular expression and language. So we'll have a start state. It can have 0 or more times of A's and B's. So that can be represented as a loop. It can be A or B. Then we can have A. Then we can have A. Then we can have A or B. So this is the NFA. Since this is a final state, we can represent it using a double circle. We can give numbers for the states 0, 1, 2. So here also in this NFA, if we see, it is non-deterministic. If we see from the state 0, on input A, it is going to state 0. From state 0, the next state is 0. Similarly, from 0 on the same input A, it goes to 1 also. So on the same input A, it has two next states. From 0, it is going to 0 as well as it is going to 1 on input A. So this is not a DFA. Let's try to draw the DFA. Now let's try to write the strings of this language. So the language says the second character from the right is an A. So if we take a minimal string AA, in this the second character from the right is an A. The last character can be either A or B. So one possible string is AA. Another possible minimalistic string is AB, because here also the second character from the right is an A. The last character is a B. So both these strings are minimal strings. We can also write more strings satisfying this condition, in which the second character from the right is an A. All other characters can be anything. So we can write A. This is also possible, because in this string also we have the second character from the right is an A. We can write AAB. This is also a possible string, because here also the second character from the right is an A. We can write AAB. In this string also the last character is B, but the second character, what we are concerned is the second character from the right should be an A. The second character from the right should be an A. We can also write BAA. This is also a possible string. The second character from the right is an A. We can also write BAB. The second character from the right is an A. We can write BBAB. In this also the second character from the right is an A. We can write BABAB. In this string also the second character from the right is a A. Let's try to draw the DFA for this. We'll draw the DFA for the minimalistic strings. We have two minimalistic strings here, AA and AB. So we will draw for that A, and this will be an accepting state. And also we have another minimalistic string, which is AB. So it can either end with A or with B. So both are accepting strings. The only condition is that the second character from the right should be an A. So here we are ensuring the second character from the right is an A. The last character can be either A or B. Now if we see before this, we can have either A or B. Before this second character, we can have either A or we can have B. So if we draw like this, A or B, if we draw like this, it will not be a DFA, because from this stage we will number the states 0, 1, 2, 3. So from stage 0 on input A, we have transitions to 0 as well as to 1. So two next states for the same input A. So this is not possible. So we cannot draw like this. We can have only B here. We can have only B here. This is only possible. We cannot represent A here. So what can we do? If we have strings like A, B, if we have strings like that, initially it can have the initial state is 0. From the initial state 0, we can either have B 0 times or any number of times. So if we have the string A, B, the first A will go from state 0 to state 1. On the second A, it goes from state 1 to state 2, but the third A is not available. So what we can do is, from state 2, we can draw another transition labeled A. So if we draw like this, now also if for the string, if we take the string A, here also the second character from the right is an A. So if we see that, you can see here from 0 to 1 on input A it goes from 0 to 1. On the second input A it goes from 1 to 2. On the third input A it goes from 2 to 2. So in this string also the second character from the right is an A. So any number of A's, 4 A's, 5 A's, if we go on adding A's, only A's, all strings of having only A's, in that case also the second character from the right is an A. So this is acceptable. Now if we take BAA, that string, for the first B, the transition is from 0, state 0 to state 0. The second character is A, so the transition is from 0 to 1. The third character is A, the transition is from 1 to 2. So here also it is satisfied. Now if we take the string if we take the string BA, B, in this string also the second character from the right is an A. If we see the transitions for this string, the first character is a B. The transition is from 0 to 0. Then the second character is an A. The transition is from 0 to 1. The third character is a B. The transition is from 1 to 2, 1 to 3. The fourth character is an A, but there is no transition from 3 on A. So we will add that one. We will add an A. B, A, finally B. So this is satisfied. Now if we take the string A, B, in this string also the second character from the right is an A. In this case, for the first A, the transition is from state 0 to state 1. For the second A, the transition is from 1 to 2. For the third A, the transition is from 2 to 2. Fourth character is a B. For that there is no transition, but this is a valid string. So we need to add that transition also. So from here, from state 2, we will add a transition on input B to state 3. So in this case, AA, AB will be also be represented using this DFA. So we have represented all these strings, all possible strings in this DFA, and we can also see in this DFA on a particular input from a state there is no more than one next state. For example, is state 0. If you see on input A it goes to only one state 1, on input B it goes to only one state 0. If you take state 1, on input A it goes to only one state 2, and on from state 1 on input B it goes to only one state 3. From state 2 on input A it goes to only one state 2, and from state 2 on input B it goes to only one state 3. From state 3 on input A it goes to only one state 1. So all these transitions are according to the rules of the DFA, hence this DFA is right. Hope this is helpful to all of you for your exam preparation. Thank you.